Hello, I'm Susan Nash, AAPG, and I'm really happy to be here today with Hugh Winkler, Factor Technology, and he's going to talk to us today about automated geosteering with Bayesian Networks. Welcome, Hugh.
Hi, Susan. Thanks for having me.
You're welcome. Well, how did you get interested in geosteering?
Well, I had I had rough exposure to it while we were running a little company called Wellstorm back in the mid 2000s to the early 2010s, and all our customers were doing geosteering, and I got to look over a lot of people's shoulders while they were doing the. Our company was in the business of delivering the real-time directional surveys and LWD data to the geosteerers, and so I would look over our customers' shoulders from time to time and observe their processes. So I could see that geosteering was sort of on the critical path during this horizontal drilling boom. It was amazing that we had all this automation in place, and then we had this sort of human high judgment, high cognitive function geology process in the middle of it.
Oh, right.
And so it seemed like an area that could profit from automation is one way to put it, but another way is just computing. Like when you talk about, I came from a seismic background as a grad student and early professional, and nobody calls seismic processing automation. They just call it computing and making a seismic image. And
Well,
that's probably the.
let's take a look at your slides and let's see the geosteering problem.
Oh, okay.
And jumping in here.
There we go.
Good.
If you're familiar with the problem, and if you're not, let me just describe what it is. You're drilling typically a 2-mile lateral, and all you have to work with are your LWD gamma ray usually, and the directional surveys. And you started this project with some idea of what the geology looked like as you're drilling horizontally, but you don't have a precise idea. And you want to position your wellbore fairly precisely within this zone of within your target zone. And when people first started doing this in factory mode in the late 2000s and up to now, they've adapted these sort of heuristic interactive tools. They've built better and better desktop workstation tools to help you do the job, but they don't really do any they don't really help you solve a math problem that gives you the most probable answer. They help you make judgments. So just to kind of state the problem, we're going to try to compute the answer that human interpreters interpret. We're going to give at least as good an answer or better, and we're going to be able to do it faster in real time with a computer. So the first step in that is to state the problem. And if you're given a type log, and if you're given some prior idea of the geology structure, and if you assume that the structure is going to vary laterally, mostly by dipping or faulting, and we're going to observe the LWD gamma ray typically and directional surveys, and we're going to use all that to compute the estimate of the true geologic structure. And if I can introduce a couple of guys that, there's 300 years of technology behind our approach.
That's great.
Yes. Thomas Bayes formulated Bayes' rule which is a rule for inverse probabilities. You know, if you know the conditional probability that something's going to happen given some condition, well, Bayes' rule tells you how to find out what the condition was, what are the causes of the observations you're reading. But using that formula directly on even a smallish size problem, the combinatorial explosion is impossible to keep in a computer if you do it naively. But Judea Pearl, back in the middle 80s, was a machine learning researcher, is a machine learning researcher, and has been working on this for 30 years, and formulated a way that we can solve Bayes' rule for these complex, immense networks of random variables. And they've been using it in machine learning and refining it for 30 years and robotics and autonomous vehicles. And if you look at those problems, they have a lot of similarities to the problem we have in geosteering.
Mm-hmm.
So I published this paper about 3 years ago in Geophysics that takes Pearl's approach, the Bayesian network approach, and models geosteering as a Bayesian network. And then John Firestein and Philip Strauss and I went off together and had the crazy idea to found a company commercializing that technology.
I love it.
So that's what technology is. And it's come a long way in the 3 years since I published that paper. And so we're committing to practice, and there's a lot of refinements and improvements, and, you know, cutting to the chase. This is an example of what we compute.
Wow,
And,
that's amazing.
yeah, this display is pretty rich with
It
information.
is.
And parts of it are like something you'll see in a conventional geosteering program. You know, let's see, I have some, there we go. You'll see on the left, you see the type log correlation, and I'll tell you about that in a minute, but that's basically that's the geologist model for it's typically a real well log, and it's the geologist model for what the vertical stratigraphy looks like in this area. And then along the top, we draw the LWD correlation and the LWD log, and superimposed on that, we draw a correlation that I'll tell you about in a second. And this blue line, this blue area, this blue zone is our computed geologic structure. This is the estimate of the most probable geologic structure that you're drilling through. And keep in mind, this is able to be computed real time as we're marching along.
That's incredible.
And thank you. Up to this point, everything you've seen is, everything I've described is pretty much a standard geosteering application view, with the difference that the computer interpreted that blue zone instead of a person. But then the thing, you know, and something that's really a new concept is that in addition to drawing you the most probable structure, we can also give you an idea of alternatives based on the real probabilities that we're computing, you know, given the LWD that we're seeing and all the engineering constraints. And usually, most of these, you know, if you're in an area like the Permian, they're pretty vanilla, and they mostly don't give you a lot of alternatives. But right here in the middle right section of the screen, you can see a divergence, and there's an alternative interpretation that's about 15 or 20 feet shallower than the blue line.
Wow, so this really helps you with geohazards and well integrity.
I think that you could use it for applications like that. If you were, you certainly want to be able to, you want to be certain that you're, there's a lot of cases where you're trying to keep the wellbore inches from the top of your zone, but you must not veer into, out of it. So yeah, geohazard is a big application. You need a heads up if you're about to head out of zone. So in this case, I think you could make an argument that even though the blue line is the most probable answer, that big thick yellow zone might be an alternative and good interpretation, because that yellow bright probability is very broad. So it means that it might have any particular choice you pick through there has is going to be close to a good answer. So this is just by way of showing that, we automate the process, but we also give you information that you can use. We clarify the choices for you so that you can apply your judgments and use, quantitative probabilities to make your choices.
Wow.
So now I've moved on to this is some very recent work. In the last 3 to 4 weeks, we've just begun making our first new interpretations using a new fault model. So I just want to make sure it's clear that we don't just need a bunch of continuous horizons to do these calculations. We can also calculate through really challenging faulted geology. And the big innovation here is that we're using a power law fault model, so that you can describe to us, before we start drilling, you describe what's the fault regime like? Are we going to see, how many faults am I going to see across this 10,000 foot lateral? What's the range of throws I expect to see? And you kind of give us that sort of fuzzy general knowledge, and we turn that into a probability distribution based on a power law, meaning that it's probable, there's a lot of papers that have confirmed that if you see, if you have, there might be 10 10-foot faults for every 100-foot fault. And there might be 10 1-foot faults for every 10-foot fault. So that's my automatic, so my timing slides move me on automatically here. So that's about it. We're a little company here in Dripping Springs, 30 miles west of Austin, and come see us.
Well, this is great. Well, what are some of your goals for the future?
I think that in 10 years, everybody will be doing, I don't think anybody will be doing manual geosteering the way they used to do it. The way to regard this is as an assistant. And this is a way to scale your geologist and make them able to delegate the rote work to a computer and let them do high-level geology.
And that's great, and have it get a little bit more sleep.
Yes, and so who's gonna, 10 years from now, nobody's, we can already see other companies trying to emulate what we've done here. Nobody's even attempted the thorough rigor that we put to the problem, and they're unable to get as good answers. But 10 years from now, that'll be different, and there'll be a lot of companies out there and nobody will be doing it the old-fashioned way. Everybody will be computing their geosteering interpretations. So we hope to be the market leader there 10 years from now.
Oh, that's great. Yeah. Well, thank you for a wonderful presentation and well, thank you for going into some of the details, because I think that they're extremely helpful. And for anyone who's watching, we've been speaking with Hugh Winkler at Factor Technology and talking about geosteering basically driverless cars for geosteering. Anyway, I really love it. It's very impressive. And
Hey,
thank you.
thanks.